Thank you for the overview. So, what do you think is the timeline that you view for the development of quantum computing? Should we expect sudden press announcements regarding the breakthroughs or more steady progress?
Okay, so obviously we're going to see sudden press announcements, exciting press announcements. But the question is how what's the size of the jumps that they are announcing, and I want to explain a little bit my point of view about this. And I think so I think there are sort of two different timelines that one can think of. First, there is the timeline that describes the evolution of the hardware. This is a tedious task to improve the gate fidelities. I'm not an experimentalist, so this is not my task, but it's clearly a very, very difficult task. In particular, the 2-qubit gate fidelities, which are the main pain to improve. And of course, the increase in the number of qubits with that as good fidelity as possible. And I think that in both superconducting qubits and in ion traps, we've been witnessing amazing advances, but they're sort of one step at a time. And I don't think we should expect these numbers to suddenly improve extremely drastically. Neutral atoms, they also show remarkable improvements recently, as we've seen. But again, I don't think we can expect that one day in the near future we'll just see a fault-tolerant computer with a full-fledged computer, and suddenly that the gate fidelities will have improved by very large factors overnight. What we actually see in hardware are smaller steps that experimentalists are heroically working on. But then there is another timeline, which is extremely important. And this is what we can do with using these steadily improving quantum computers. Meaning, I'm referring now to the quantum advantage timeline. This is what I'd like to call it. And this corresponds to what circuit volumes and what algorithms are available at any given moment using current devices. And this is where, in that timeline, this is where the mid-stack role comes in very strongly, because software can make here a huge difference. So let me explain a little bit about that quantum advantage timeline. I think it's useful to mark 3 sort of quantum advantage milestones in this quantum advantage timeline. So the first can be called initial quantum advantage. This is the ability to run the first quantum circuits, which cannot be simulated efficiently by a classical computer. So basically a rough number would be to run general quantum circuits on, say, 50 or 60 qubits, and maybe roughly 1 or 2,000 gates, 2-qubit gates. And this is already something that is hard for classical computation. So this would be initial quantum advantage. And then the next step is, say, 100 qubits with roughly 10,000 gates, 10 to the 4 gates. And let us call the ability to run general circuits on these numbers broad quantum advantage. And these numbers probably are not sufficient to say replacing classical algorithms used in, say, the pharma or in chemistry industry by quantum algorithms. But it still already is of huge interest because it could provide these kind of numbers of 100 qubits with 10,000 gates. This would provide quantum designers an enormous edge over classical algorithm designers. If they have access to a quantum computer, this would allow them to develop their algorithm using simulations on quantum devices in regimes where it would be completely impossible to simulate for classical computers. So they can use their quantum computation access to understand how their quantum algorithm would scale and how it behaves. And that would be completely impossible without access to a quantum device. So that's the second milestone. And then there is a third milestone, which is already arriving at ROI quantum advantage, return on investment. So this will be the point where the first few quantum algorithms arrive, which are already ROI. And it's the point where we can start seeing the first quantum algorithms, which can replace classical algorithms used by, say, a fertilizer company, replacing them by a quantum algorithm. So for computational tasks that they use to develop their products. And it is estimated that this ROI will only start with quantum algorithms applied on at least 200 or 300 of qubits, if not more, and maybe 10 to the 5 or 10 to the 6 quantum gates, if not more. So these are already large numbers. Now, it is not that I think, it's not that I think that we can hope for a sudden jump in the quantum advantage timeline either, but the software is going to help us push these timelines to accelerate the timeline of the quantum advantage. So achieving each of these milestones requires further improvement in the hardware, and it will take time. But I certainly think that with good software, we can achieve these milestones significantly faster than we actually currently estimate, much faster than just waiting for full-fledged quantum fault tolerance to appear.
Thank you.